In Essential Task 2.3, we are going to continue talking about different forms of research and specifically talk about what's called correlational research. Similar to what we did with descriptive research, we're going to be talking about the purposes, the strengths, and of course, the weaknesses of correlational research. I advise a horizontal piece of paper for this concept map. The concept map involves the box at the top, which is going to define correlational research and identify the strengths and weaknesses. And then we're going to be talking about these 4 columns across from left to right. A couple of the columns look somewhat tall. They're not quite as long as they look, though, from afar. Like this one look here looks really big, but there's some pretty large pictures there. But as a whole, I think holding the piece of paper horizontal can fit all of the information that you need for this concept map. So I'll give you a moment here to pause so you can copy down the yellow portion of the essential task. As I alluded to, we are going to start here at the top and first talk about what correlational research is. Correlational research is a new unique type of research, so it's not that descriptive technique that we talked about in Essential Task 2.2, but correlational research is this unique type of research that's designed to determine whether or not 2 variables fluctuate together, or do they vary together. And what that means is when we identify 2 specific variables, do they have a relationship where they both increase together, perhaps they both decrease together, or maybe there's what I like to call an up-down relationship, which we'll talk more about when we get later on in this concept map. So, for example, does the amount of time you spend studying, does that correlate with your GPA? Do both of those values or those variables increase together? More than likely they do. Does the amount of time every week that you spend sleeping, does that at all correlate with the amount of hours a week that you work? Perhaps those have some type of relationship. Perhaps as one increases, the other decreases. That's what I mean by fluctuate. We're just trying to make predictions for future research because it's often the case that you find some type of unique correlation while conducting this type of research that can then inspire and lead you to conduct an actual experiment, something we'll be talking about in the next essential task. I cannot stress this weakness enough. This is arguably one of the most important things I'll teach you all year. But just because 2 variables fluctuate together, meaning they're correlated, does not definitively prove cause and effect. Cause and effect, as we'll talk about in the next essential task, is a really important point in research, but it requires an experiment or some type of randomized controlled trial. Correlational research is not sufficient to prove cause and effect. If I can kind of show you this in a really funny way. But let's take a look at these variables. The amount of cheese consumed is correlated with the amount of people who have died by being tangled in their bed sheets. Those 2 variables have fluctuated together since 2000. We're not, though, going to take this data with this graph and say that cheese consumption is causing people to be killed by their bed sheets. That would be an asinine statement. But just because 2 variables are correlated doesn't mean there's a cause and effect relationship. The more divorces in Maine, or rather, as the divorce rate drops in Maine, people are eating less margarine. Those are correlated, but that's not cause and effect. The less people getting divorced isn't causing people to eat less margarine. That would be an insane statement. But those 2 variables fluctuate together. The amount of people who are killed by venomous spiders and the length of the word in the script spelling bee, that winning word, those are correlated. But we're not saying that venomous spiders are causing the words in a spelling bee to go up and down. That's ridiculous. But those variables do fluctuate together. People who have drowned falling out of a fishing boat and the marriage rate in Kentucky are correlated, but nobody's going to claim that one is causing the other. This might be the best of them all. The more movies Nicolas Cage appears in, the more people who are dying in swimming pools by drowning. We're not saying that Nicolas Cage movies are causing people to drown themselves in swimming pools, but those variables technically do fluctuate together. Those ones are all ridiculous. I'll admit that. But the whole point for correlational research is to just find whether or not variables fluctuate. And even though variables fluctuate, doesn't suddenly mean you can say one causes the other, just as those ridiculous correlations indicate. In terms of actually preparing and setting up correlational research, we're going to start here in the bottom left and talk about methods. This box is a little bit tall, not super long, but it does have some information on it. It's going to transition a little bit below, so don't close the box just based on what you see here. To actually conduct correlational research, the first thing you do is pick 2 very specific variables, because correlational research always works with 2 very distinct variables. So you can evaluate height, weight, happiness, salary, you could get IQ scores, you could get a self-esteem value, you could get the amount of hours a week on average you study, the amount of hours a week on average you sleep, the amount of days per week that you work out, whatever it might be. Once you've determined your variables, height, weight, exercise, whatever it might be, you need to produce what are called operational definitions. Because just because you say height doesn't necessarily always indicate precisely what you're studying. There are a lot of different ways to calculate height. And if you're going to use height as a variable, you need to be very specific. You need to inform the reader of your research that you're talking about inches. You need to specify whether a person's going to keep their shoes on or not. Those are all very important criteria when defining something like height. An operational definition is a very precise measure of a variable. It takes a topic like height or weight or happiness and turns it into a numerical value. When you work with correlation, everything needs to be turned into a numerical value. So even something like salary needs to be turned into a numerical value, and you need to specify. We're talking about yearly salary before benefits. It's an exact description of how the measure of the variable was determined, and it allows future researchers to replicate or to repeat your work, which is essential in research. Just to give some examples of operational definitions, height could be inches without shoes. A term like happiness or stress doesn't by default have a numerical value attached to it. You can ask somebody if they're happy or not, but that doesn't have a number value to it. And correlational research needs a number value to work. So what you can do is you can make a 1 to 5 scale and present that scale to your participant and say, based on this scale, what numerical value would you attribute to your own happiness, or maybe your stress, or it can be your self-esteem. So you can use topics that don't necessarily by default have numerical values, like happiness, stress, and self-esteem, if you turn them into some type of 1 to 5 or 1 to 10 scale. And then once you've identified your variables, and again, you're only picking 2 with correlation, height and happiness, height and stress, etc., then you need to get a random selection of people to partake in your 2-question correlational research. So you could ask these randomly selected people, what is your height? And using my 1 to 5 scale, evaluate your happiness. Or maybe, what is your weight? And on 1 to 5 scale, evaluate your stress level. Or it could be other things. It can be, on average, how many pairs of shoes do you buy a year? And we can take that numerical value and we can see whether or not that fluctuates with a person's weight or height or salary. Once we've taken the time to identify 2 variables, height, weight, spending habits, self-esteem, happiness, stress, etc., then we created an operational definition, which is an extremely precise way of turning it into numerical value. 1, so that your research is clear, and 2, so that other people can replicate it. We then continue onward. Once we have acquired our randomly selected data, we then use what's called a scatter plot to graph it. A scatter plot is used to graph correlation. That is precisely what it's going to be used for. And it's a really quick visual representation that allows you to determine if the 2 variables you selected have a relationship with one another. Do they fluctuate? Do they go up together? Do they go down together? Does one go up and the other go down? Or is it kind of all over the place? So you can very easily see in that bottom left corner that the scatter plot indicates some type of upward slope. That would be an example of 2 variables that do have some type of strong relationship. We would call those variables correlated. While the scatter plot to the bottom right corner and sort of the all over the place nature of the results would indicate no relationship, or at least very little relationship, which would mean whatever those 2 variables happen to be are simply not correlated with one another. But scatter plots are going to be specifically used to graph correlation. So not bar graphs, none of the other types of graphs, not a distribution curve like we're going to talk about later. We're talking distinctly about a scatter plot for correlation. Moving into that 3rd column, beyond just using a scatter plot, so a visual representation of correlation, there is a numerical value that we use to measure whether or not the 2 very precisely defined variables that you've been studying have a correlation to one another. And we use what's called the correlation coefficient. It's a single number, and that number is going to range anywhere from -1 to +1, and then anything in between. And it's actually really easy to work with, and it's really easy to tell if 2 variables are correlated once you're given this number. And this is how it works. If the correlation coefficient that you have been provided is close to the number 0, it means the 2 variables that you're studying are not closely related. The closer the numerical value is to either +1 or -1, the stronger the relationship is between those 2 variables, meaning they are in fact correlated. So if you are provided a correlation coefficient of 0.97 or -0.97, those are extremely close to either -1 or +1, and that would indicate to you as the researcher that you have 2 variables that do fluctuate together. However, if you received a correlation coefficient of 0.05, that's almost a zero. That's incredibly close to zero. That would mean that the two variables you're studying have virtually no relationship with each other, none whatsoever. And as this visual indicates, and I actually honestly think it's worthwhile to copy down this visual, as it indicates, it doesn't matter if the value that you were provided is positive or negative. The further you are to the polar extremes of this visual, to the negative one on the left and the positive one on the right, the stronger the relationship is. The closer you are to the middle, to that zero, the weaker the relationship is, the less the two variables that you're studying fluctuate. And the College Board loves to ask this, but occasionally they'll provide you a multiple choice question and it'll have 5 values. And the question will be, which of the following indicates the strongest correlation? It doesn't matter whether the value that is provided is positive or negative. That has a totally different relationship here. We'll talk more about what that positive and negative is in just a minute. But it doesn't matter. Whichever one is closer to either negative one or positive one would mean it has a stronger relationship. So negative 0.99 would indicate a stronger correlation between two variables than positive 0.98. It's very common for students to see the positive and negative and have some sort of other prior knowledge that they apply. It's not applicable here. Negative 0.99 is stronger than 0.98 because it's just a little bit closer to negative 1 relative to 0.98 is to the actual number 1. The positive and negative just indicates the direction of the relationship, the direction of the fluctuation. So, for example, a positive correlation. So the reason why a number would have a positive attached to it. So whether it's positive 0.14 or positive 0.97, it's because if you were to graph that on a scatter plot, you would have this upward slope, indicating that the variables have what I call an up-up relationship. A positive correlation is an up-up relationship. So two variables that increase together. So for example, the amount of time you study is probably correlated with your GPA. As one increases, the other is more likely to increase. I'm not saying it's causing the other to increase. That's a leap that we cannot make with correlation. But just if it's graphed on a scatter plot, you would have this up-up relationship. Alternatively, a negative correlation has what we call an up-down relationship, meaning as one variable increases, another variable decreases, an up-down relationship. Self-esteem and self-assessed depression are a good example of a negative correlation. So if you have sort of a 1 to 10 scale on self-esteem and a 1 to 10 scale on depression, you're probably going to get these results, where the higher an individual evaluates their self-esteem, the lower they evaluate their overall level of depression. That's a good example of a negative correlation. As one value increases, another value decreases. Occasionally, students are curious, well, what's a down-down relationship? Well, you're not often going to hear it worded like this, but a down-down relationship is technically a positive correlation, because if you can go up the slope, that also means you can go down the slope. So, for example, as stamp prices get cheaper, that probably means we're further back in history. So a down-down is actually just another way of describing an up-up. So don't get confused with negative correlation. Negative correlation is when one value goes up and another one goes down. The value that we were talking about earlier, that negative 0.97 or negative 0.98 or 0.15, those individual values can all be attributed with different scatter plots. So, for example, to go back up to this visual, you don't have to copy anything else down on your concept map, but just to stress this point. And we made a comment how these extreme values, the ones closer to positive 1 or negative 1, indicate strength of correlation. They all match up with what scatter plots would look like. So a 0.0, no relationship whatsoever, would look like something here on the top left corner. A 0.3, which isn't very strong, sort of has a positive correlation look to it. Or rather, this is a negative 0.3. Kind of has a downward trend, not by a lot, but by a little. Negative 0.7, that's a little bit stronger. You notice that downward slope. Negative 0.99 is almost a perfectly straight line. So that individual value that you were provided correlates to a scatter plot. And you can clearly see that this one, with a correlation very close to negative 1, is almost a perfect downward slope, a perfect line. Continuing onward, there's one final box that will conclude our discussion here of correlation. So far in this essential task, we've identified that correlation is two variables, numeric variables, so we have to turn them into numbers. Those scatter plots don't work if they're not numbers. You have to operationally define them, meaning you have to come up with a very precise way of determining that numerical value. So height without shoes in inches, for example. You get some randomly selected data, so you get some random people to question. And then from that point, you throw it into a scatter plot, and you get a correlation coefficient that tells you whether or not the two variables fluctuate together. There are, though, a couple issues to take into consideration. The first is what we call the third variable problem. You don't have to copy what's in this sort of black box in the middle. That's just an example of the third variable problem. But there is a reason you can't look at two variables and whether they fluctuate together and definitively show cause and effect. There's a reason we're not going to jump to that. The first is that you never know whether or not a third variable is present, meaning there might be a variable that you haven't considered that might be influencing the fluctuation of the two variables that you are studying. And because you can't rule out potential third variables, you're never going to look at two variables and say cause and effect, say causation, just because they're correlated. Because, for example, ice cream sales and shark attacks are correlated. I could graph those in a scatter plot and you would see a positive correlation. The more people buy ice cream, the more people get attacked by sharks. But nobody is going to definitively say that sharks are somehow attracted to ice cream or that ice cream attracts sharks. Nobody's going to make those conclusions because any logical person would look at those and say, well, more people go to the beach during the summer. Maybe being at the beach is somehow influencing the likelihood of shark attacks. So I'm not going to in any way, shape, or form to say that shark attacks are causing ice cream sales or vice versa. There's probably a logical third variable, in this case temperature, that reasonably explains that situation. So although that data might be interesting, nobody is saying shark attacks cause ice cream sales. That'd be absurd. That's an example of the third variable problem, where just looking at correlational research cannot definitively prove cause and effect because there's often many third variables that you're not controlling for that can reasonably explain your findings. That's why we have to wait for experiments in the next essential task to use the word cause. The final thing is that often people also find what we call illusionary correlations, where they don't run the numbers and they sort of just have this gut feeling the two variables are correlated. Like every time it rains, I feel like my joints hurt. A lot of people will say things like that without ever actually running the data. That's another good example of two variables that might not actually even be correlated, but because you sort of have that inner belief, sort of that gut feeling, you present it as some type of correlation. And oftentimes people present it as some type of cause and effect, that the rain and the bad weather causes my joints to hurt. That's another example of jumping to conclusions that are not likely backed up by the data. We call that an illusionary correlation. When you believe that there is a relationship between variables, when you have a belief that they fluctuate together, either positive up, or negative up, down, when there more than likely isn't if you were actually to run the numbers. So there's quite a few reasons why just because variables fluctuate together, we can't definitively, concretely, from a scientific-minded perspective, say there's a cause and effect relationship. As we proceed into the next essential task, though, we will talk about the steps necessary to actually say studying causes an increase in grades, or sugar causes or maybe sugar doesn't cause hyperactivity. We'll be able to directly address head-on that question of cause when we come back in the next essential task and talk about experimental research.